Welcome to Navigating NEXRAD. My name is Scott Denstead. I'm a CFI and former National Weather Service research meteorologist. And I'm also EAA's subject matter expert on weather. And I'm a co-author of Pilot Weather from Solo to the Airlines. That was co-authored with Doug Morris, who is a Boeing 787 captain for Air Canada. The website is pilotweatherbook.com. I'm going to give you an overview, introduction to how you should approach your pre-flight weather briefings. And then we'll dive into convection and turbulence. The reason why we look at NEXRAD is so that we can better understand the threat of convection and turbulence. So we're going to also talk a little bit about lightning and what that can tell you, and when it's missing, what it can tell you as well. So also we're going to get into the details of the NEXRAD basics. It's going to cover a lot of topics. And then we're going to finish up with two items, specifically looking at how to use NEXRAD to identify various different convective hints, especially in cases where lightning isn't present. And then I'm going to go over and do an overview of cell movement, what that means to your NEXRAD display. And if we have time at the end, we'll talk about and have some questions. Well, first of all, the big picture is critical. I know anybody who's heard me speak on the topic of weather knows that I really emphasize the need to understand the big picture. Certainly, I'm not saying that details are not important. They are very important, but the big picture is the king. When I do my own pre-flight briefings, the big picture gives me more information about that go or stay decision than the individual details. So when you look at this particular image, you're seeing a pickup truck who is evidently maybe turned over and broke through the guardrail. Certainly that driver was very lucky, but it's not until you see the big picture that it really comes into focus. So again, details are important, but that big weather picture is the king. So I get a lot of questions about, Scott, what is your pre-flight briefing? What is your strategy for going through the weather? Is there any special thing that you do? Well, I tell everyone that I use a funnel approach. And that is, I start with the big picture. Again, that big picture is so critical. And there's more decisions I've made because of what I've seen in the big picture than any of the details combined. So the big picture is really where you should start, in the top of the funnel. And then you can work your way down toward the details. You can look at terminal forecasts. You can look at a NEXRAD mosaic. You can look at METARs. You can look at SKU-T diagrams, whatever it is that provides the details that kind of fill in the gaps of what the big weather picture doesn't. And ultimately, pilots need to learn how to extract truth from all those imperfect forecasts. We know for sure that as soon as those forecasts go out, they're imperfect, but there's a lot of truth, there's a lot of usefulness to those forecasts. And it's a really good idea to learn how to extract all that truth. And I'm not going to be able to cover all that in detail, but we're going to provide some of that throughout this particular program. It's also important to understand from a pilot's perspective that weather is not, weather forecasts are not about being black or white per se. It's all shades of gray. So it's important to understand that, we're dealing with uncertainty. And then longer range forecasts, those 3, 4, or 5 days from now, those are going to have a lot more uncertainty. And as you get closer to your time of departure, that nowcast kind of fills in all those kind of details, the bottom of the funnel kind of details that you learned in your short range forecast. So I spend most of my times, for instance, if I'm traveling, let's say tomorrow morning, I'm going to spend most of my time, probably an hour's time, the night before, to understand what that big picture looks like. And that way, when I wake up in the morning, I'm not doing a lot of extra analysis. Instead, I'm kind of filling those final details of what those short range forecasts tell me. And that's where I will pull up the latest NEXRAD image. I might pull up the latest METARs and the latest TAFs, look at the pilot weather reports. And those are going to be a lot more reliable than those longer range forecasts. All right, so next let's talk about convection and turbulence. So turbulence, specifically we're going to talk about today, convective turbulence is really what we're trying to avoid. Sure, there's other turbulence that's non-convective that we want to stay away from, but tonight we're going to be talking about convective turbulence. And so the ground-based radar image that you look at, whatever favorite one you look at for your pre-flight or even in flight, doesn't really definitively tell you that there's going to be turbulence or not. But it will provide us with some clues. It will show us certain signatures we want to avoid and be more careful with. So what causes turbulence? Well, it's actually pretty simple. It's atmospheric mixing. Well, simple to say, but there's a lot of details involved. We only feel turbulence. We only feel turbulence in the cockpit when it occurs on the scale of the size of the airplane. Essentially, that means when we start to see eddies that develop in the atmosphere that are about the size of the airplane, that's when we'll actually feel bumps in the airplane itself. So the example I generally give is, imagine you're driving your car over a gravel driveway, and the gravel, let's say, is a silver dollar size or something like that. And the car will drive over pretty nicely. It won't bump around a whole lot, and you'll hear the wheels crunching underneath the gravel itself, but you won't necessarily feel bumps per se. But if you take a little remote control car and you drive over that same gravel driveway, you'll notice for sure that that car is going to bump around quite a bit because it can feel those actual individual pieces of gravel because they're closer to the size of the scale of the vehicle itself. Now let's take that same situation. Let's take your car and drive into one of the supermarket parking lots where you have these big, huge speed bumps. And if you drive your car fast over that, you're going to feel it. Because again, that speed bump is closer to the size of your car. Now, if you run that remote control car, a very tiny remote control car, over that speed bump, it won't feel the bump per se. It'll rise up and down over it and feel the upwash and downwash, if you will, but really won't feel the bump because, again, that's not quite the size of the scale of the vehicle. So when we look at things like thermal turbulence, we have this rising, expanding air, and it has a wake associated with it, and the prevailing winds interact with that particular wake. So you have that prevailing wind that's going to be interrupted. All that process, all that mixing, interacting with the prevailing winds, produces turbulence on the scale of the size of the airplane. And as a result, that's what we feel in the cockpit. Now, if you had a big mountain wave, let's say crest-to-crest wave of a kilometer or two, in that case, it's a lot like driving that remote control car over the speed bump. You'll feel the upwash and downwash of that mountain wave, but that's technically turbulence, but you just don't feel it. You may be very laminar flow. Now, if that wave breaks up and starts to develop into a breaking mountain wave, then we'll eventually create eddies on the scale of the size of the airplane. So in order to interpret any ground-based radar, you really have to, before you get started with that, you really have to quantify the risk of convection along your route. That looks basically looking at that big weather picture. So you want to look for signs of convection, look at convective outlooks prior to flight, but also while you're in flight. You want to look at the clouds. You want to examine what's happening there. You want to see that if you have a vertically developed cloud, clouds with very hard edges, those are convective clouds. And that's when they start getting deeper and deeper, that's when we worry about running into severe or extreme turbulence. Now, in this particular webinar, we're not going to focus on what's the look and feel outside the window per se. We're going to focus on the products themselves. So you really never can separate convection and turbulence. Sure, again, there's turbulence that occurs that's not convectively related, like clear air turbulence, for instance. But when you start talking about convection, turbulence should be the next thing out of your mouth. And so we know that convection is the vertical transport of heat. And essentially, think about it as a result of an imbalance to solar heating. So the sun beats down on the earth, there's an imbalance produced, and Mother Nature essentially convects its heat away to reduce that imbalance. Or you can have the case where You have something called baroclinic instability. Now, big words, but ultimately this is the pole to equator instability that occurs. So the poles are very cold and equator around the tropics are very warm. Again, that creates an imbalance, and that's what essentially causes our major weather systems to occur. You got major upper level troughs that bring cold air down from north to south, and you have these upper level ridges that push warm air from the south to the north, and that's that baroclinic instability. And there's two types of convective turbulence that you're probably familiar with, and that's essentially the dry or invisible convection that occurs. That would be essentially below the cloud bases. And if you've ever flown when it's a kind of a warm, hot day out in an area where the turbulence is very common, essentially that's going to produce your dry thermal turbulence, and that's those bumps that you feel while you're a couple thousand feet off the ground. But when that air eventually saturates and reaches saturation at the base of the cloud and produces visible clouds that, as you see here there behind, those cumuliform clouds, that's essentially what we call moist convection. And then when that moist convection gets really deep, that's when we can start to talk about essentially deep convection or thunderstorms. Right, speaking of that, let's talk a little bit about lightning. So we know that a thunderstorm technically involves the presence of lightning. No doubt about it. It's the definition of a thunderstorm. But I like to think about convection as more of a generic description of the process we just talked about. And that is, I'd rather pilots use the term deep moist convection rather than thunderstorm. That really describes the process in place. So when you look in that picture in the background there of that very billowing cumuliform clouds there, that's essentially deep moist convection. You've got some depth to the convective process, and it certainly is going to produce some significant updrafts, and I definitely would not want to find myself in the middle of that. Although essentially that may not have any lightning in it. So what do you call something 1 second before the first lightning strike? It's really technically not a thunderstorm. It's called a rain shower. So even showery precipitation, whether that's precipitation, a forecast you might see from a terminal forecast or even in a surface observation, all those elements, anytime you hear the word shower in any kind of forecast, that's a good indication that you've got a convective process in place. It may not have lightning associated with it, but it may still be very dangerous to fly through. So lightning itself basically suggests you have very cold and very high convective cloud tops. You have a depth to those clouds. And that implies you have significant vertical mixing. There's that mixing process, atmospheric mixing that's occurring, and that may cause severe or extreme convective turbulence. So anytime you see that, you're going to be also worried about the possibility of low-level convective wind shear. You might have a gust front or outflow boundary ahead of that convective situation. Again, you might have lightning with it. You may not necessarily. But if you do, you're obviously going to be dealing with the possibility of convective wind shear. Now, it may be the case that gust front is 10, 15 miles ahead of the primary rain that you see on your NEXRAD, but ultimately you may still have wind shear as you are approaching the airport and well ahead of any precipitation. So lightning comes in two basic flavors: cloud to ground and intra-cloud lightning, or you may hear that as cloud to cloud lightning. Now, it's important to understand the difference here because many locations around the U.S. have actually like a 10-to-1 ratio of intra-cloud lightning to cloud-to-ground lightning. So, for instance, if you are in the northern and central and southern plains, especially central plains, you're going to see on many cases there's going to be 10 intra-cloud strikes to 1 cloud-to-ground strike. Or if you're in maybe the Great Lakes area or Ohio or Tennessee Valley or in the southeast, you're going to see more of a 2-to-1 or even a 1-to-1 ratio in some cases, or even in the Intermountain West where you see more of a 1-to-1 ratio. So it turns out that many severe storms with a high flash rate, lots of lightning strikes, are dominated typically by intra-cloud lightning. So often it's more than even a 10-to-1 ratio in some of the severe storms. And the brief period where you can actually see a ratio that's infinite, meaning basically all intra-cloud lightning and not a single cloud-to-ground strike. And so I think it's important to be able to see both cloud-to-ground and intra-cloud lightning. And that's where I think the SiriusXM product is much more superior than the FISB in terms of being able to see all the kinds of lightning strikes, not just those from cloud to ground. So again, lightning requires that there be three things simultaneous in the clouds, and that is supercool liquid water, ice crystals, and what's called graupel or soft hail. All three of those need to be in the cloud at the same time, and if for some reason there's insufficient quantity of one or more of these things, that's going to limit the ability to have lightning. And a lot of times you have essentially low top lightning, low top convection, I should say, low top convection, which may not have any lightning at all. So it may not have enough ice crystals or enough graupel in the cloud at the time to produce lightning. There may be plenty of supercool liquid water, but if you're missing one of those other two items, in that particular situation, you may not get lightning, but that does not mean that that particular situation, that particular cloud, isn't dangerous. It certainly could be. And when we talk about low top convection, we're talking about like 25,000 feet or lower. All right, let's delve into the NEXRAD basics. So NEXRAD is a network of ground-based radars. Now, I say network in quotes because it's really not networked together like you might think of, but essentially these are a bunch of NEXRAD sites that provide data that can be actually sewn together, as we'll talk, into a mosaic. It provides both what it's called surveillance and Doppler radar data. And so that includes things like reflectivity for the surveillance portion, as well as velocity for the Doppler portion, and something also called spectrum width. Now, of course, the NEXRAD radars scan the entire atmosphere. They make multiple 360-degree sweeps. And those elevations occur from everywhere from even a negative 0.2 degrees to 19.5 degrees. And we call that a volume scan. It turns out that for years it was only down to a half a degree at the lowest elevation, but they'd been experimenting with actually lowering the lowest elevation down as far as minus 0.2 degrees, like for instance out in the San Francisco and the Bay Area. And the radar sends out a pulse of energy, and that strikes airborne objects. We typically call those hydrometeors. And of course, those radar pulses get reflected back. We call that backscatter, and that backscatter is measured and recorded in what's called decibels of Z, or dBz. And so for your next hangar party, you can impress all your friends, all your pilot friends, that you can tell them that in 1 hour of the radar operation, it's only on for about 7 seconds, and it's listening for 59 minutes and 53 seconds. So a lot more listening is going on than actually transmitting. And so each elevation scan produces a base reflectivity product. I know this is a misnomer. A lot of people think base means lowest. It does not mean lowest. Every single elevation angle produces a base reflectivity product. So the word base actually comes from the word base data. When I initially told you about that there was reflectivity and velocity and spectrum width, each one of those essentially are the base data of which you can produce other products from that base data. So base does not mean lowest reflectivity, in this particular case, lowest elevation. So this is quite important here, and I don't think it's really provided as training to many pilots, but reflectivity is actually on a logarithmic scale. And that is, it's the reflectivity parameter, or Z in this case, is determined by the sum of the 6th power of all drop diameters in the volume. So that's affected by the number of drops, so the total drop concentration. So you got the more drops that you have in there, the higher the reflectivity. And also the size or the diameter of drops are really important. That tends to be the dominating factor. So when you get really large drop sizes, and we expect that in convection or thunderstorms, drops tend to coalesce into larger and larger drops. That means we likely have some pretty serious weather to deal with. But you can also have a situation where you have lots of smaller drops, still have pretty high reflectivity, but not have much in the way of significant turbulence because of that. So a 3 millimeter diameter drop actually returns over 700 times as much power, reflected power, as a drop which is only 1 millimeter in diameter, even though it actually contains 27 times as much liquid. So when you get larger drops, you get higher reflectivity, and that makes sense. When a thunderstorm or in deep convection, you expect larger drops in that situation. You got an updraft going, and the drops are going to coalesce and produce those larger drop sizes and therefore higher reflectivities. So essentially, reflectivity increases really quickly as those drop size grow. So even if the total amount of liquid water in that volume doesn't really change a whole lot, but the sizes grow, you're going to get higher reflectivity. So again, larger drops are a sign of that deep convection and probably dangerous turbulence. Once you start getting above 50 dBz, the drop sizes are large enough to potentially produce dangerous convective turbulence. However, as I said before, you can actually get some pretty significant amount of reflectivity with a lot more, a case where you have a lot more smaller drops, more on the order of 40 to 50 dBz, and the turbulence actually might be minimal. That's why it's real important to understand before you depart, what is the convective potential? Go out and look at the convective outlooks to see, am I going to be flying through an area that is prime for that deep moist convection? And there are basically two different reflectivity products that you'll see. And that's the composite reflectivity, and that's basically, imagine that you're looking at the entire column of air above a certain point, and you're trying to find what is the maximum value in all the base reflectivity points in all the elevation scans. Whatever that maximum is what they're going to use for the composite reflectivity. And of course, the base reflectivity, typically the one we see is from the lowest elevation scan or lowest tilt. And that's usually representative more of what's happening, kind of what's falling out of the base of the cloud. So again, every single elevation scan has a base reflectivity of the product, but the one we typically see is the lowest elevation or lowest tilt. It's also important to understand the differences between a composite and a base reflectivity, and that is composite reflectivity typically has a much larger footprint. So when you look at that, often it's looking at the higher elevations in the radar scans, and it's probably seeing some ice crystals in the storm's anvil, and that tends to reflect energy. But it also could be in some situations that you'll see some some moisture that is being carried up and held up in higher elevations. That's also a possibility. But I always say that if the lowest tilt is kind of better for pilots that are flying at lower altitudes, below those cloud bases. And essentially, that allows you to be able to kind of match up what you see on your onboard weather, your Sirius XM, for instance, to be able to see kind of what's happening outside the cockpit. I find that the picture looks more crisper, but you'll see that as this image kind of goes between the two different ones, you've got a larger footprint there for the composite versus the base reflectivity. But you can also notice here very much at the top there, the composite actually has a pretty significant area of weather that's further to the north. Again, that could be an area that's in a developing process or maybe in a dissipating process, as the case may be. You really don't know specifically from looking at that. Now, vendors use the reflectivity and possibly velocity data to then stitch all those individual radar sites together and produce essentially what appears to be kind of a seamless mosaic across the entire country. And you can see that here, but ultimately, when they put all that together, it also produces, in some cases, in some particular mosaics, it will produce all the data it sees. So it may see, in some cases, some ground clutter and such. So you'll see that some of the providers, such as SiriusXM or even the FSB, will have a tendency to filter out some of the ground clutter that occurs. And ground clutter would be things associated with like bugs and dust and debris, birds, even airplanes create that kind of ground clutter. So they go through and filter out that ground clutter to produce a nicer, cleaner view of this. So you can see in this particular case, you'll see a lot of areas around the radar sites that you can see where there are definite areas of what looks like precipitation, but that's all ground clutter. But if they remove all that goes away and only leaves kind of real precipitation. And that's quite important to pilots. They don't want to be spending a lot of time trying to figure out whether this is real or not. This allows them to clean that up. Sometimes they do a great job, sometimes not so good. One of the ones that happens a fair amount and kind of slips through sometimes is this concept of anomalous propagation. So the radar beam can actually be ducted and reflected off of non-airborne objects. And usually that happens when you have a low-level temperature inversion in place. And that temperature inversion super refracts the beam, and the side lobes of that radar beam essentially bounce off of objects and come back to the radar. And when that happens, you may get some really interesting results. For instance here, anomalous propagation can really look a lot like real precipitation, even look like convection as the case may be. So if you were here at Indianapolis and were trying to depart to the east, you may think twice about it, but it turns out that most of what you see here is that anomalous propagation. It's not real. The only area shown there circled in white is actually real precipitation. So it's important when you look at NEXRAD, also compare it against other products, like simply look at a satellite image to see what's happening there, or look at surface observations in the other areas to see if they're actually producing any kind of rainfall or thunderstorms or anything like that. So let's talk a little bit about convective outflow boundaries and gust fronts. So we have a situation where we have a building thunderstorm, we have air rising, expanding, and cooling, producing that convection, that deep moist convection. We also have air that essentially is flowing outbound out of that particular thunderstorm. And so this is the exhaust of a thunderstorm, and it comes down and actually strikes the ground and moves outward, sort of like pouring pancake batter on a griddle. And it moves outwards and acts like an outflow boundary. And these actually show up pretty nice on the radar depiction if it's unfiltered. This is why filtering sometimes is not always a good thing. And in most cases, when you're looking at a data link NEXRAD depiction, because it's a light-looking precipitation in terms of it's not heavy precipitation in terms of reflectivity, it'll end up typically being filtered out. So you can see that kind of crescent-shaped outflow boundary that's occurring there. And again, that can be seen on many different sites, but you have to make sure that it's essentially unfiltered. And it usually will show up pretty nicely when it's close to the radar. These outflow boundaries tend to not be very high up. So if you are essentially getting a situation where the outflow boundary is probably going to be 6,000 or 7,000 or 8,000 feet above the ground. So if you're flying higher than that, you're probably above that particular boundary. But essentially lower than that, especially close to the convection that's producing that outflow boundary, it can be quite turbulent at times. The further that boundary moves away from the core thunderstorm that produced it, the less threat it will be. And lastly, let's talk about convective hints in cell movement here. So one of the things I always impress upon all of my students is to make sure you continue to look at more than just the NEXRAD image. So in this particular case, when you see METARs that have multiple layers, or even terminal forecasts that forecast multiple layers, a few scattered or broken, that's indicative that you have a convective process in place. And also remember that showery precipitation, SHRA, also is a good indication you have a convective process in place. And that doesn't mean thunderstorms per se, but this still could be a very nasty event to fly through. So all those convective hints are there for you. And also when you look at a particular NEXRAD image, kind of look at it from the standpoint, does it look like somebody splattered some paint on it? So they put a paintbrush in, put a bunch of different colors in red, yellow, orange, and blue, and splattered it onto the canvas. Is that really kind of what it looks like here? Or is it more like a brush stroke kind of a thing? So ultimately, paint splatter look to it is going to be defining a convective process in place, whereas a brush stroke means you're less likely to have any kind of convective turbulence. But again, you want to make sure you do your pre-flight analysis to determine if this area is ripe for convection or not. So you then definitely want to take clues from the wide view. Don't go too far in and zoom in on an area when you're flying along. Take that big picture view of what's going on. And that way you can then spot kind of that cellular appearance to the NEXRAD depiction. And lastly, let's talk a little bit about cell movement. So what drives the direction of the movement of convection? Well, it's actually two things. It's the movement of the air mass as well as the upper level wind. So the movement of the air mass kind of moves the line, in this case moving the line from the kind of northwest to kind of southeast here. And the winds aloft tend to take the individual cells and move them along that kind of more of a northeasterly track. And you kind of think of this as each of the individual cells I'm showing there, kind of like a railroad car on train tracks. But imagine them, instead of the tracks being fixed, the tracks are actually moving along with those cells. So in many respects, what you end up with is the individual cells themselves will be a combination of the movement of that air mass as well as the winds aloft, although the winds aloft are probably more dominating in most cases. So when you are looking at the winds aloft to determine maybe how these are moving, again, it's going to be a combination of these two particular vectors that's occurring. Also, you can see, like for instance with SiriusXM, storm tracks, and they show the speed and direction of movement of any kind of significant cells. And they also show you the ecotop heights, the top of that precipitation core. And it's not unusual sometimes, as you see in this case, that the arrows kind of point, that are adjacent to each other, kind of point in opposite directions. That happens quite a bit. And that could be because in some cases, it could be that these are from two different radars and they're trying to get an assessment for what's going on there, and they're just not doing a great job one radar to the next. Or in most cases, especially in initial development, when you're starting to see convection just starting to blossom, it may actually interpret, for instance, an area that's rapidly developing next to an area that may be dissipating. It sees that development as maybe movement of that cell. So anytime you're seeing the initial stages, especially in what we call pulse thunderstorms, or what colloquially is called air mass thunderstorms, where things are starting to develop, you may see a very hodgepodge of where these particular arrows are pointing. But ultimately, once that convection gets really going and has a good movement and is very mature, those arrows will point in the right direction. So what's the best approach to circumnavigate convection? Well, I always like to fly on the upwind side of the cell. That's where it's usually a lot more stable. So here's an example from a instrument flight that I was taking with a student. We were coming from New Orleans, headed back into West Houston Airport. And there was two cells. There was one up to the north near Bush Intercontinental Airport, and one down further south near Houston Hobby. And in this particular case, the controller wanted us to squeeze us between the two cells. And that made sense from an air traffic standpoint. Wanted to be between the two major airports. That's the typical situation. They bring you down to 2,000 feet and squeeze you between the two airports so you can stay out of the way of any other traffic departing or arriving into those two airports. But that wasn't working for us. Now, the approach control radars are actually pretty darn good. They're dual fan beam Doppler weather radars, in addition to being able to track aircraft. So, and they are quite up to date in terms of that. Maybe not so much so in center, but for the approach control radars, they're actually pretty darn good from that standpoint. But you can see here our direction of flight, where they want us to squeeze us through in these two cells, wasn't really comfortable for me. In fact, this is kind of what we were seeing outside the cockpit. We were seeing this wall of clouds, and that just didn't make any sense to me to try to squeeze between the two. And yeah, there were a few glimmers of open, of non air area where you didn't see any cloud, but that was really, really narrow. And with the movement of that convection, I wasn't comfortable with it. So I know that these cells, and I've been watching them, they were moving to the north. So the one around Bush Intercontinental Airport was heading to the north, and so was the one around Houston. It was moving to the north as well. So we just asked for a vector around the southern side, essentially away from it. So the cell was moving away from us at that particular point. And you can also see any of the plus signs, the yellow plus signs. There was definitely lightning. These were cells that were fairly mature, but we definitely were not going to try to squeeze between them in the upwind side of the one cell that was further south. And this shows us that we were pretty darn close. It looked like we had one wingtip, if you will, in the main part of that cell. We were pretty far away from it. And also the delay essentially is somewhere in the order of between 5 and 7 minutes now. Essentially, you're looking at the possibility of that cell moving further away from you. So I can guarantee you we were in VFR conditions in very smooth air at 2,000 feet, working our way around this particular cell, headed back to West Houston. All right, that's all, folks, and we'll go ahead and take any questions. Again, if you're interested, Pilot Weather from Solo to the Airlines and Soft Cover and ebook now available for purchase at pilotweatherbook.com. Thank you.